Let's look at running a hypothesis test when we have two distinct populations whose means we would like to compare. So in this case, population 1 is a group of students who had some extra math activities, and population 2 is a group of students who did not have any extra math activities, and then they took some sort of test and we averaged out their test scores. So we took 47 students in the first group, 38 in the second group, found their sample mean and sample standard deviations. So we're hoping to run a hypothesis test at the alpha equals 0.01 level, so the 0.01 significance level or 1% significance level, to determine whether those extra activities actually made a difference in average test score. So we're going to do this not by hand, but using a function in our TI-83 or 84 calculators. So to find this, we're going to go to stats and then tests. Then we're going to figure out which of these tests works out best for us, which one makes the most sense. So for starters, we have two different means. We know that because two distinct populations, and there's no reason to pair up students in these groups. So this is not a paired situation. It's two distinct populations, two distinct means. So we're going to say, okay, well, we have, first of all, two sample. And then we've got two choices for hypothesis tests. When we're dealing with two samples, we can either run a z-test or a t-test. And for us, that distinction is going to be made by the fact that we have S, the sample standard deviation, instead of sigma, the population standard deviation. So we're going to run a two-sample t-test since we have S. Now, if we run that, most of the information that it's going to ask for is in this table here. Now, it's not necessarily in the same order, so be careful about that, because the first thing that the two-sample t-test is going to ask for is the average for really group 1, sample 1 here, and then the standard deviation, and then the sample size. So just be careful that when you input these values, you're putting them in the right order. Now, the other piece of this is figuring out, well, what's our alternative hypothesis? So our null would be that there's no difference between these two. So the null hypothesis, if you're writing this out, is just that mu1 is equal to mu2, or another way to say that is that mu1 minus mu2 is 0. It's another way to say that. This is particularly helpful if you're trying to connect your hypothesis test to a confidence interval, because a confidence interval is usually looking for this difference. So if 0 is in the interval versus not in the interval, that kind of ties into what we're doing here. Anyway, our alternative hypothesis, well, we want to look at the wording in particular. So if there's some reason to believe, based on the wording, not based on our gut feeling, based on the wording, that mu1 should be greater than, less than, then let's use that. Otherwise, we just say not equal to. So mu1, mu2, let's figure out what that relationship would be. Now, our gut would probably tell us the group with activities. We're kind of curious if mu1 is greater than mu2. However, the wording here says we want to determine whether those activities made a difference. Made a difference. So that leaves open the possibility that the activities actually hurt the students. So we just want to know, is there some difference? Is mu1 not equal to mu2? Or another way to say that is mu1 minus mu2 is not equal to 0. Okay, so when we run through the two-sample t-test, where we have the option, right, and the reason I wrote these out is because when we're in that test, we have the option where it's going to ask us about mu1 in relationship to mu2. So specifically, it gives us mu1, the way that looks is, it says mu1, and then it gives us the various options. So it gives us not equal to mu2, it gives us, let me just make sure I got the right order, less than mu2, and then greater than mu2. So we're going to select that first one, right? mu1 is not equal to mu2. And then after that, it's going to ask us if these are pooled. In general, unless you are told otherwise, we're going to say no, these are not pooled. So if we run through that, again, we have to input all that information, but if we run through and calculate this, then we're going to get a p-value of, well, let me erase this here. So we're going to get a p-value from all of that of 0.01328, blah, blah, blah. So it keeps going. The most important thing, though, is we make a comparison between our p-value and our alpha. So p right now is greater than alpha, which is 0.01. Remember, alpha is like the cutoff. So this is the place where we say, okay, if our sample results occur less than 1% of the time, right? Meaning incredibly rare, less than 1% of the time, then we believe our assumption is incorrect. Right? We have enough evidence, we have statistically significant evidence to say our assumption, the null hypothesis, is not correct. Unfortunately, our p-value is bigger than alpha, so we don't have enough evidence. So we would say, okay, since p is greater than alpha, there is not sufficient evidence to reject the null hypothesis, meaning we fail to reject the null hypothesis. That's another way to say that. Now, remember, we never embrace the null. We never say the null is true. This is just like in a courtroom, we say guilty or not guilty. We never say innocent. So we never say that the null is true. It's just that we didn't come up with enough evidence to reject it, to say that it is false. So in this case, remember our null, so think in terms of context. So our null was that mu1 equals mu2. Basically saying that the average test score for population 1, the group with activities, was the same as the average test score for group 2, those without activities. Again, we can't claim that is true, but what we're saying is there's not enough evidence to say it's not true, to say that these made a difference. Now, we may want to rerun this test and think to ourselves, okay, why would we have the activities and then just think there's some sort of difference, right? This is probably more of a one-sided test instead of, as it's written, a two-sided test, right? So a one-sided test would say, hey, we think these activities helped. And so we would think, as an alternative hypothesis, mu1 is actually greater than mu2. And if we ran it through like that, our p-value actually would be smaller than this alpha. And you can run it through and double check, just change from a two-sided to a one-sided. So in that case, right, depending on one-sided versus two-sided, it can make all the difference as far as whether we reject the null hypothesis, or in this case, we fail to reject it, we don't reject it.